So, welcome everybody to Approaches to Parallelization in C#, which I could have called multi-threading, and I really wish I had have done now, because I can't even say the word. However, it's a really important concept, and one I think most people will be familiar with to some degree. And whilst it is a common concept, I think it's worth revisiting first principles as to sort of why we parallelize. And in a nutshell, doing one thing is generally pretty easy. Whether you're calling a REST API or resizing an image or updating a data field. And as soon as you try and do it 10 million times, it becomes a lot less easy. You can have the world's most optimized API call that takes 800 milliseconds. Seems super fast, but unfortunately doing that 10 million times takes nearly 100 days. And not to mention the sort of CPU that takes up, CPU cores, and it's a whole world of different challenges. And in order to do these things efficiently, we need to be doing many things at the same time. So most introductions to multi-threading and parallelization will split tasks into two different kinds. First up, CPU-bound tasks. And these are ones where the task itself is tied to the CPU speed and really the power of the underlying hardware. They're tasks that do lots of things. They could be doing calculations, they could be resizing images, but typically they take up a thread in the underlying operating system. So multiple cores, multiple threads in a CPU can help with greater concurrency. RAM often has a big impact. And for me, the way I remember these sorts of tasks, they're ones that are typically restricted by the hardware of the local machine. You will run out of RAM or you'll run out of CPU before you get to all of the tasks. Second type is an I/O bound task. And these are tasks that are bound by input and output. And really what that means is anything that requires reading and writing data, anything that goes over a network, internet connection, something that relies on bandwidth. And these typically don't take up kernel threads. They don't take up threads in the underlying hardware, and C# is very good at allowing a lot of these to be run simultaneously using await, async and await. HTTP client, great example. However, what you'll find is limitations are generally hit by remote servers. There could be all sorts of different reasons, but the key part of I/O bound tasks are they're restricted by the hardware limitations of a remote machine. Basically something that is not under your control. Now, whilst that is how every single multi-threading or parallelization tutorial starts, it's very rarely that simple. Tasks, yes, you can categorize them as CPU bound or I/O bound, but actually there's so many other things that impact the design of a good parallel system. Third-party limitations, restrictions on concurrent connections, licensing. IIS on a desktop supports 10 concurrent connections just because of licensing. State management, it's managing kind of shared resources between systems, knowing when things are finished, and even the underlying protocols used, like HTTP, HTTP 1 versus HTTP 2. It has a massive impact on how you design a parallel system. I'll go through a real-world example at the end, but before that, I want to take 3 approaches to parallelization that I tend to use in every parallel system I put together. So just before we go into those 3, I'll take you through the demo system that I've put together to show how these work. Now what this is, it's a really basic API, web API, that simulates a long-running request. Now hopefully you can see that, but if you can't, effectively this takes a request and sleeps a thread for between 5 and 10 seconds. Nothing complicated, but just something that takes long enough that we can see multiple tasks running at the same time. And it comes with a beautifully designed dashboard that shows all of the running requests. And what I will do is give a quick demo of said dashboard. So this is just a test console. It's calling that API. Every time I hit enter, it's sending a new request. So we can see straight away that's running concurrent requests, they're coming off. And that's what we're going to be able to see how the actual parallel programs work. I'll let them finish, otherwise it will mess my database up. So first up, parallel for each. Arguably the simplest approach to parallelization in any system, any language I think I've ever come across. You take an enumerable list. For this example, generating a list with 100 items in it. What those 100 items are is totally irrelevant. I'm going to pass them into my parallel for each loop, and it's going to loop through and do the thing in parallel, which sounds vague, and it is. And this is one of the problems with parallel for each, which we can go through shortly. But first off, here's what it looks like in action. So the loop of 100 items has been initialized, and that parallel for each is running through, and it's executing a long-running request a number of times. And what it's actually doing here is it's trying to figure out the CPU limitations of the underlying machine. It's probably slightly difficult because we've got the web server and the calling threads running on the same machine. But ultimately, it will run as many threads as it thinks it reasonably can at one time to complete the tasks. And so pretty quickly, you can see those 100 items have been completed in, I don't know, however long that took, 60 seconds, maybe less than 60 seconds. Other than this last one. I have to let it finish, otherwise it's going to, again, mess my database up. So, lots of good things about parallel for each. It's really simple. I'm going to say it automatically optimizes for CPU usage. I've done a lot of research into how it does this and what it does to do this, and there's just no clear documentation that I can find on what, why, and as a result, it doesn't feel like there's any fine-grained control over concurrency, which for me is a big problem. Slight caveat about these results is parallel for each is optimizing based on CPU. The long-running task, whilst it's sleeping a thread, it's not strictly CPU bound, so these results might look a bit odd. But really for me, there's just too many unknowns. Not having that fine control doesn't sit with me. I'm too much of a control freak, and so I don't generally use this approach. Next up is a slight variation on a similar thing, which is something I'm a lot more comfortable with, called a semaphore. Now, Semaphore is one of the real base classes in multi-threading, and it's a flag effectively used to count access to a shared resource. Now, in this example, and in C# in general, Semaphore Slim is a simple implementation designed to be used in a single thread, and it allows a much more controllable approach to multi-threading while still having a lot of the benefits of a parallel for each type loop. So before we show the example, I'm just going to take you through this code. First up, initialize the Semaphore Sim with the max concurrent locks. We've gone for 10 in the example. This code here then waits for a resource lock to become available on the semaphore. And you see it's an async task, it's not tying up a thread. However, it is blocking execution until one becomes available. Next up, we're running the actual request itself on a brand new thread using task.run. And when the request has finished, which is executed synchronously, we're releasing the semaphore. And importantly, because each task is running on its own thread, we need to wait for those tasks to finish, otherwise there'll be no master thread for them to run in. And it also provides another really useful method within C#, which is task.whenAll. And that takes a collection of tasks, which we can see is the result of each one of the semaphore release tasks, and we'll wait for all of those tasks to complete. And so that allows you to insert some parallelization in the execution flow of a standard program and then carry on synchronously afterwards. So, let's have a look at what that looks like. So using exactly the same code from that example, the console, it started, it's initiated a collection, 30 items, and again, it's looping through each of those, but it's never going to hit more than 10 concurrent requests. And then as the locks get removed, they all get completed. And so for me, that's a really important differentiator between semaphores and Foreach, because it gives the really fine-grained control over concurrency and direct access to the tasks returned, allowing us to use things like task.whenall, or we could batch tasks up. And again, runs on a single execution thread, which is good for simplicity. However, does have drawbacks when you start looking at system resources. They're always going to be the things that limit your maximum level of concurrency. CPU, RAM, storage, anything that sits on your local machine. Final approach I want to look at is queues. And a queue is designed to really come in two parts. One is the population of a queue. In this example, we are sending messages or adding an item to a queue in a simple loop. Now, in reality, any system could add an item to a queue. It's an HTTP call, it's an API call. The key thing is that the system adding the item to the queue is totally separate to the queue. Separately, we have consumers, and this is an executable program which is receiving a message from the queue and effectively allows us to control the threads even more manually. Now, each one of these queues is a single thread. It's receiving a message from the queue, it's processing that message, and then it's waiting for the next one. And so kind of core to this is the decoupling of concurrency from the underlying hardware. The queue sits separate. In this example, it's an Azure queue, sits in Azure storage, and can be accessed by any system and allows us to have many consoles or many consumers running on many different platforms, which looks something like this. Right, so first up, we've got to fill the queue with 30 items, which is pretty unexciting. But we can see nothing running. So next up, we start one consumer. That is analogous to one thread, and that's going to go through, it's going to process, and we could let that process 30 items and it will take some amount of time. However, if we then want to control the concurrency, we'll start a few more instances. With each one of the consoles running, effectively being a thread, allowing us to control the level of concurrency, but also this could be running on a different machine. It could be running on a different data center. And really any of the hardware limitations that exist, whether they're bandwidth, whether they are CPU or RAM, they can be handled with a pattern somewhat similar to this. Okay, so really to sum up a queue, each individual task runs in a single execution thread. However, they can be deployed across multiple machines, multiple times on one machine, and typically a combination of both. Now, one of the downsides is this, it really does add significant complexity to state management. And for state management, there's a couple of ways of looking at that. There is sharing of resources, HTTP state cookies, could be entity framework, anything that you'd want to use a sort of a singleton pattern through dependency injection becomes very difficult when you're talking about different machines, whereas it's trivial when you're looking at the first two examples. And also overall execution state. Knowing when all those tasks are finished, because there is no single thread that can carry on synchronously, requires a separate system to monitor the tasks, to look at them and to actually do something when they're all finished, if that's a requirement of the system. So, they're the three approaches to parallelization that I would typically use in any system. And yeah, fairly straightforward. However, like any Hello World tutorial, when you start to build a real system, it's very rarely that simple. So as a demonstration, I've come up with a great idea for a very simple website that allows you to search the internet. Definitely hasn't been done before. And we're going to call it Sopro. And the purpose of this is it's going to crawl the entire web to discover websites, and it's going to save it all in an easily searchable database. And a couple of ways it's going to do it. We're going to start off with an initial list of domains. I've got 100, 200 websites written in a notebook. Feels like a good number to start with. Each one of those, we're going to visit the home page. We're going to extract all of the URLs from that page, add it to a queue. We're also going to find any new domains and add them to our original list. And we're just going to carry on processing both of those queues until they're empty, until we've got no more to go through. And that process will look something like this. And yeah, really, you're going to start here. We're going to have this queue, which is URLs within a website. We're going to get the next one and carry on until that's empty, whilst at the same time adding any internal URLs into this queue, adding new domains to this queue, and carrying on round until we've finished the entire internet. Now, the problem with this is there's a lot of websites. The internet's pretty big. So we're going to need more than one machine to do it. And whilst we're going to use more than one machine, actually on each machine, if we're just going to do one page at a time, that's also going to be inefficient. We're going to have most of that machine's resources being used for nothing. Another thing we want to do is maintain session state across a website. What we do, we might have a list of 10 pages. We don't want to visit each one of those pages as a new visitor. And we decided we want to run JavaScript. We want to use cookies. We want session state to be maintained. So every single website needs to run in its own execution thread. Coupled with that, websites really don't like too many concurrent connections. It's the basis of a DOS attack. There's lots of security in place. We don't want to look like we're trying to take websites down. And so taking all those requirements, there's no one single approach to parallelization as we've defined it that would fit. However, a combination of these things allows us to solve this fairly complex problem, which would look something like this. And just before I go through it, black code, this is not real code. I probably wouldn't use HTTP client. I might use Flurl. However, it is so. This is like a pseudocode representation of a domain crawler. And what we can think of is this is a console. It would run on one computer. It could run on multiple computers. But core, we've got a domain queue, which is separate. And so each one of these crawlers is going to get the next domain from the queue. It's going to initiate a second queue locally and start that with the home page. Next up, we're going to initialize a browser. It's going to satisfy all the requirements of cookie containers, maintaining session state, and then we're going to use that same browser with our semaphore to handle max degrees of concurrency to process each page with that domain URL until the internal queue is empty, at which stage we get the next one from the domain queue. So really we can build on those resources to do it. Yeah, that's it. And before everyone runs off and starts to build the next generation search engine, anyone got any questions?
I don't know if we have the time to ask all of them. So, what about utilizing the thread pool that is controlled by the operating system instead of Semaphore Slim? You can queue an item in a thread pool. The operating system will handle maximum number of threads, maximum executions.
Again, I think this is one of those theoretical versus real world scenarios. There's very few scenarios where the thread pool or the number of threads is the limit. In almost all cases I've worked on, it's been a server, so it could be rate limiting or throttling on an HTTP request. It's been a database, so you're actually having to monitor the database on an external server and look at the CPU and RAM usage, or it's CPU and RAM usage in the local machine. So in all of those cases, it's necessary to control the level of concurrency to manage those external resources. Doesn't have to be Semaphore Slim, it could be consoles and a queue, but as soon as you don't have that control and you're just relying on the thread pool to limit it, you've just taken down the database server.
Okay, next one. How would you compare using, let's say, I suppose this is a pseudocode example, not a real code, but I haven't seen an example of thread-safe variables, let's say. We want to avoid that while loops or Foreach or whatever. How would you compare parallelization, let's say, with the data flow library that Microsoft offers? Everything is under the hood, everything is asynchronous, you can await things, and you have a broadcast block which can broadcast whenever it receives some information.
It sounds very good. I've never used it, but I will certainly look into it.
And the last one, that logo seems quite familiar on the search engine. Are we sure we won't get any trademark issues?
No, absolutely not. I've checked and there's nothing similar. I mean, obviously I couldn't search too much because there's nothing to search that exists. I had a quick look.
Thank you.
Anyone else? No, so thank you very much. The code is available on GitHub if anyone's interested. I've removed any keys to storage that might have accidentally been pushed. But yeah, other than that, thanks a lot and let's go for a beer.